Let's talk about operations. What are the kind of operations you can do on a signal? You can add it. And this is how we show signals being added. Let's say, just as an example, we have X signal X that is 4, 2, 9, 8. We have signal Y that is 6, 2, -1, -1. I'm going to say, let's say it's zero centered over there. Really quickly, how would I get my Z? I'm going to ask Gordon.
Yes.
How would I add those two? Both finite time sequences.
Finite time would just add them together like normal numbers.
Okay, so what would be my first number?
Depending which ends line up, sir.
Right, exactly. So now what's my first number?
In the case of X and Y, it would probably be 4 and 6.
So what's my first number in Z?
10.
No, because you were right the first time. It depends how they line up. And where are they lining up? You've got this.
Oh, I see. Yeah,
4, 2, 9, 8. This is for n equals 0. So this would have to be -1, -1, 2, and 6.
So your first number is 1 then.
No. So now let's add these guys up. Here's my X, and here's my Y. So now add them up. We got 6.
6, 6, 1, 8, 8.
Okay. And where's my 0 point?
Is at the 1.
That's it. Oh, I see what you meant when you said, what's my first number? My first number in the sense of n equals 0 is 1.
Yes, that's what I was going off of.
I've got you. Okay. So not much more.
I have a question.
Shoot.
Why did we shift over the Y one left?
Because our arrow points to our 0 index.
Oh, okay. Thank you, sir.
Yep. It would probably be, maybe it would be even clearer if I graphed them. So you've got this 4, 2, 9, 8. But this is 0, 1, 2, -1. And then to that, we're going to add this other guy, which its 0 index is at -1. -1. And we've got our 2 and our 6. So maybe now it's clearer how we're going to add the corresponding pieces. Okay, so that's addition. I'm not going to talk about subtraction. It follows. We can do, in MATLAB, if you had it, you would have to do a little bit of creative zero padding there. In MATLAB, you would have to say that X is equal to 0, 4, 2, 9, 8, and Y is equal to 6, 2, -1, -1, 0, where we've added in those. And you add it in so that you've got -2. I'll just do the shortcut for it. -2 to +2. And so you zero pad it so that you could plot a n comma x or a n comma y, and they'd both be valid plots. And now you could simply say z equals x plus y and stem n comma z, and it would work. So those are your MATLAB commands. Let's talk about another one. There's multiplication. In DSP we call it modulation. And same idea, except we're just going to have the multiplication symbol. I won't talk about that anymore. That's multiplication of two signals. But you can also multiply by a coefficient, by an unchanging coefficient, and we show that with a triangle. So this would be multiplying every input number by negative 3. There's the delay operation. The delay operation is shown by a z to the negative 1 power. So as an example of a delay, if we have that signal going into a delay of 1, we'll have, we will have this signal coming out of it. So this is 1, 2, 3, and this is 1, 2, 3. Whoops. Man. It's a little scary. Let's try that. Okay. There is an advance operator, and that would be a z to the positive 1. And you can see how that works. So let me give an example. We were talking about what's a differentiator before. I'm going to build a differentiator right now. Differentiator. I'll take my signal x of n, and I will add it to a time-delayed version that I then multiply by negative 1. So by multiplying it by negative 1, I'm subtracting it. And let's see what this does. If I feed it an x of 0, 1, 2, 3, 4, 5, and so on. What will my y be? Okay, so to figure out what's going on here, we've got to firstly set things up. What was my x before time equals 0? Guess I need to show where my time is 0. We're going to start it off here. So if this is our 0, we're going to assume that our input was 0 before that point. In other words, we're going to assume that our system starts totally at rest. In other words, we're going to assume that the previous input was also 0. If I was to graph it, we'll assume that it looks like this. And now all of a sudden it will start to go up. So since we assume it was 0 before time equals 0, then it would have, if it was, the delay says its current output is its previous input. I'm going to write that down. Current output is equal to the previous input. That's what a delay That's what a delay is. So if its previous input for all time was 0, then its current output will have to be a 0. Multiplied by -1 will give us a 0. For time equals 0, for our very first value, we have a 0 in, and so our very first value out is also going to be a 0. Let's see what it is for our next value. For n equals 1, now we've got 1 going into it. Fawaz, what's our output of our delay?
It would be a 0.
It'll be a 0 because its input just before was a 0. So its previous input was a 0 at red, so its current output will be a 0 multiplied by -1 is still a 0. Now we've got 1 plus 0, so now we've got a 1 out of there. I'm going to do it for one more, and then I'll let you go. And that happens to be the end of the class. I'll have ever so slightly more stuff on the video, another 1 minute after you go. In fact, if you'd like to go now, just go now. I'll continue solving the problem, and then I'll put it on video. To find out what it is at 2, I'll change color. To find it at 2, now our input is at 2. Our output of our delay was whatever our input was at the previous sample. Well, our input was 1, so now our output is a 1. That gets multiplied by a 1 to be a -1. And now we have 2 minus 1, so we have a 1 for our next sample. Our next input will be 3. The output of our delay is whatever the input was just before, which was a 2. Becomes a -2. Now we've got 3 minus 2, which is also a 1. And you can see by that argument that our output stays a 1 forever. So our output looks like this. And if you ask yourself, what is the derivative of this? The slope here is always 0. It's 0. The slope here is a straight slope of 1. So it's 1. So this is a discrete time derivative function. And if you want to see what its impulse response is, you could instead feed it an impulse. And if you fed it an impulse, you would get this diagram over here, which is the impulse of a discrete time derivative function. Okay, that was a lot of stuff. There's one last device, one last system, and it's called downsampling. And in downsampling, we have a input, and it goes into a downsampler by M. It's easiest to show what a downsampler does with an example. Let's say we've got a signal that looks like this, and we feed it into something with a downsamples by 2. What it does is it takes every other value and throws it away. So it passes our n equals 0, it throws away our n equals 1. It takes our n equals 2 and throws away our n equals 3. So if we had more over here, it would pass this and would pass our last 0 and give us this. You can have a downsample by 3, downsample by 4. It just throws away every other or every third or every fifth sample. And that's it. That's the readings. Any questions on any of that?